Alright, so here we are going over the quiz 20 answers. So please make sure if you're absent you're taking notes on this and submitting that to me to get exempt from the quiz. So here we go. Number 1 says, which of the following orders the attractive forces from weakest to strongest? And so here is the answer. It was London dispersion is the weakest. That is followed by dipole-dipole, which is followed by hydrogen bonding. And they did have one more in there, that was ionic. Ionic bonds are considered the strongest of the bunch, and so obviously the wrong choices had those in different orders. So that was number 1, orders of attractive forces from weakest to strongest. All right, number 2, former College Board question, has a figure, and so to sketch out this figure, it's got this. And it keeps going, but the relevant part is here, that it has an arrow pointing to this that says 150 picometers, and an arrow pointing here that says 100 picometers. And so the question is, the figure below shows that in solid hydrogen fluoride, there are 2 different distances between the H atoms and the F atoms. Which of the following best accounts for the 2 differences? And so the answer choice here was that the difference in strength between the covalent bonds and intermolecular attractions. The idea being here that this particular bond right here with the solid dash, this is a covalent bond. This is a stronger attraction, rises to the level of an actual chemical bond. Therefore, that bond length is shorter. Whereas over here, that dashed line for this 150 picometers, this is a hydrogen bond, which is one of your intermolecular forces, right, between 2 separate hydrogen fluoride molecules. If I were to kind of box it out here, here is one molecule of the solid hydrogen fluoride, and then here's a second molecule, and they kept the picture going. They had about 4 molecules in there with the picture. And so that's the idea, that the blue one is just hydrogen bond, which is a weaker attraction and therefore a longer length or distance between those 2 atoms. Just looking at the incorrect choices, it says accommodation of the necessary bond angles in the formation of a solid, uneven repulsion among non-bonding electron pairs, and different isotopes of fluorine present in the sample. Those were incorrect choices. All right, number 3, which of the following would you expect to have the highest boiling point? And it was all of the diatomic halogens, fluorine, chlorine, bromine, and iodine, in varying orders. And so the answer to this question was the iodine, because it had the greatest number of electrons, which meant it was the most polarizable, which means it would have the strongest IMF or intermolecular attractions, and therefore it would have the highest boiling point. That's kind of your logic in terms of an FRQ. All right, number 4. It said, in which of the following groups of substances would dispersion forces be the only significant factor? And so they had out a list here. Roman numeral 1 was chlorine gas. Roman numeral 2 was hydrofluoric acid or hydrogen fluoride, depending on what state of matter it is. Number 3 was neon. Number 4 was KNO2. And number 5 was CCl4. And so since the question asks which one would dispersion forces be the only significant force, you were looking for your nonpolar molecules. And so that was going to be this guy right here, nonpolar, NP for nonpolar. It was not going to be this guy. This is a polar. I mean, it's either a polar molecule if you consider it a covalent bond, or you could even consider it ionic to some extent, given that the hydrogen will ionize as an acid. But either way, it's not going to be an answer. This one is an answer. It is an atom, and remember, atoms will have equal distributions of electrons under normal circumstances. This one definitely not an answer. This is an ionic compound. And then this one is, it is nonpolar carbon tetrachloride, has a tetrahedral geometry that would render it as a nonpolar molecule. So that means that the answer to this particular question was Roman numeral 1, Roman numeral 3, and Roman numeral 5. All right, moving on to question number 5. It said, what type of intermolecular force accounts for the following differences? And so they tell you that acetone boils at 56 degrees Celsius, whereas 2-methylpropane boils at negative 12 degrees Celsius, and you are given these structures. So here was the acetone, right? This was given to you, and then here is the 2-methylpropane. 2-methylpropane. And then again in the question and text it says that the acetone boils at 56 degrees and the 2-methylpropane boils at negative 12 degrees. Those are the boiling points. So with that, you're looking at the fact that this has these stronger intermolecular forces, right? And so accounting for the differences here, this is a hydrocarbon, strictly hydrocarbon. This is a nonpolar molecule regardless of the branching, because there will be tetrahedral arrangements around all of the carbons. But this one, it's going to be right here. This oxygen is going to make this with its lone pairs most definitely a polar molecule. And we did see that in one of our examples yesterday, that having that oxygen in the middle, whether it's actually in the middle of the chain or whether it's sticking off like that, those oxygens with lone pairs are going to definitely throw off the polarity of the molecule. And so with that, the answer to this question, your choices were all of the different intermolecular forces, London dispersion forces, dipole-dipole bonding, hydrogen bonding, or ion-dipole bonding. And your answer was simply dipole-dipole bonding. Yeah, because being polar, this has permanent partial charges that will cause stronger attractions. Okay, so moving on to number 6. Number 6 was another picture. It had a series of water molecules where they were labeling different locations, and the question says, which of the labeled arrows identifies a hydrogen bond in water? So let's go through some of the different setups. So here was one of them where they labeled this one A. And that was not the answer because this is simply a covalent bond. That is not a hydrogen bond. All right, so then moving on, they took, let's say this one, and then they put little dotted lines here to an oxygen, right? And then they had hydrogen and hydrogen. And so there was an arrow pointing to that one. That was arrow B. And that was incorrect because that was nothing, right? You would never have the oxygens attracting each other because they would have the same charges. They would have like charges. Both of these are going to be partial negative, and therefore they would never be attracting each other in the first place. All right, then they had one, I'm just going to kind of branch off of here, where they had dashed lines going to a hydrogen, right, of another molecule of water. And so this was labeled as C, and this was incorrect because this, once again, is nothing. Both of those atoms would have the same charges on neighboring molecules, and therefore they would not attract each other. Oops, not same atoms, same charges. Yes, they are the same atoms, but that's not relevant. It's the fact that they're the same charge. That these would both be partial positive, so your partial positives would not be attracting each other. And so last but not least, you had 1, 2, 3, oxygen, hydrogen, hydrogen, and here D, this was your correct answer. This is the hydrogen bond B for 2 reasons. Number 1, it is between 2 neighboring molecules. I've boxed the 2 molecules there. These are the 2 molecules of water. And we've paired up the opposite charges, the partial positive of the hydrogen and the partial negative of the oxygen. This represents the hydrogen bond right here. So that was question number 6. All right, question number 7. Here we go. It had this picture. I didn't even really feel like the picture was necessary. It was supposed to represent diatomic bromine. Here was a Br and here was a Br, and then they had like a much larger diatomic iodine. So there, that was the picture, and it said the diagram above shows the molecules of Br2 and I2 drawn to scale. They were drawn to the same scale. Which of the following is the best explanation for the difference in the boiling points of liquid bromine and iodine, which are, they said it in the question, 59 and 184 degrees Celsius, respectively. And so given the context, this is a former AP question. This would have been mixed in with a whole bunch of other questions. So hopefully we are going to start to recognize that anything having to do with boiling points should relate back to intermolecular forces or bonding if you're dealing with ionic compounds or metals. But it's going to be those attractions. Breaking attractions is what boiling is all about. So given that the answer choices weren't too terrible, let's write down what the correct answer choice was. You guys should already be able to tell me why this one had a higher boiling point, and that is because while they're both nonpolar and they both experience only dispersion forces, or LDFs, it is the fact that the iodine has more electrons. And so here was the answer to that question. It said I2 molecules have electron clouds that are more polarizable than those of bromine molecules. Thus, London dispersion forces are stronger in liquid I2. Right? And so that was the answer, just saying the I2 have electron clouds that are more polarizable. I would have liked something on an FRQ indicating, well, why is the I2 more polarizable? And that does have to do with the increased number of electrons in their electron cloud. Right? But let's just read through the other choices so that you are aware of what not to get sucked into. One of them said bromine has a greater electronegativity than iodine. Thus, there are stronger dipole-dipole forces in liquid bromine than in liquid iodine. That is incorrect because bromine having a greater electronegativity, it wouldn't matter because it's bonded to elements that are the same. So both cases, you have no net dipole. So the fact that this one's bigger than that one, it doesn't matter. Everything is still canceling out anyways, creating no charges. So while it is true that bromine does have a greater electronegativity, and that's what College Board likes to do, is they like to put true statements, that is completely irrelevant to this idea of boiling. Electronegativity is all just about how well are the electrons being shared, are you creating unequal electron distribution. Boiling is all about breaking attractions, and those attractions are a direct result of the charges on the molecules themselves, of which these guys have no permanent charges because when bonded, their electronegativity differences are zero. So that was one of the choices. Another choice says the solid iodine is a network covalent solid, whereas solid bromine is a molecular solid. We haven't talked about network covalent solids yet, but the iodine is not, or the bromine is not a solid in this particular question. It's a liquid. So what it's doing in a solid shouldn't necessarily affect what it's doing as it's boiling from a liquid to a gas. But no, it's not the type of bonding, or how it exists as a solid does not necessarily influence what the boiling points are. Another one said the covalent bonds in I2 molecules are weaker than those in Br2 molecules. Okay, that one might have tricked you if you thought that boiling was actually about breaking these bonds. Boiling does not separate the I2 atoms from each other, right? Boiling doesn't separate the two bromine atoms from each other. What boiling does is it takes, and I'm going to add this in, it takes and it separates two bromine molecules from each other. That's what boiling is going to do. It's going to separate these from each other, which is why it's the intermolecular forces that are more important, not the bonds. Now, if I were talking about an ionic compound like NaCl and NaI, then I would look at the strength of the ionic bond. I would look at the lattice energy of these two, because the one that has the greatest lattice energy or lattice enthalpy, that one would have the higher melting or boiling point. Because in this case, the dominant force that's keeping everything together is the ionic bond. There are no intermolecular forces here within the salts. So just keep that in mind. All right, so then the last three questions was a question set. And so in this question set, you were given a bunch of information. You had 3 containers. They even told you what everything was: methane, ethane, and butane. They gave you the chemical formulas: CH4, C2H6, C4H10. And then they gave you the molar mass. So this was grams per mole, the molar mass 16, 30, and 58. They gave you the temperature in Celsius, so 27, 27, and 27. And then they gave you the pressure in atmospheres of 2, 4, and 2. So this was all the information that was provided to you in the table. And so then they started with the questions. The first question was, the average kinetic energy of the gas molecules is? And that answer is the same. The reason it is the same is because the temperatures were all the same. Therefore, the average kinetic energy is the same in all 3 containers. That does not guarantee they are going the same speed, because they are different molecules at the same temperature. However, their average kinetic energy, which is the product of their mass times their velocity squared, that would be the same. So that was number 8. Number 9 was tricky. It said the density of the gas in grams per liter is, and your choices greatest in A, greatest in B, greatest in C are the same. Those were also the choices for A, by the way. In order to answer this one, you had to look at the pressures, because if you remember, at constant volume, at constant temperature, which it were, because it says questions 8 to 10 refer to 3 gases in identical rigid containers under the conditions given in the table. So we are at constant volume and temperature, which means that pressure is directly, right? Isn't that the directly sign? I don't even know what that is. But pressure is directly related to moles. Meaning, I don't know how many moles I actually have, but it's going to be a 1 to 2 to 1 ratio. That this container actually has twice as many moles, 2 times as many moles as the other containers, just given the difference in the pressures. Right? There's so much empty space that it doesn't matter actually how many are there, or it matters how many are there. It doesn't matter how big they are, though. It just matters how many are there. And so knowing that, then, if I had 1 to 2 to 1 moles, well, just looking at the molar masses, you could say, okay, well, 16, that's the mass of 1 mole, so that would be 1 mole. But then here, 30, that actually means I would have a mass of 60 grams if I were going to have 2 moles in that container. And looking at that, then, we have 16 grams. This is grams per 2 mole, yeah? But that's what we actually have in our containers. 16 grams in A, 60 grams in B, and 58 grams in C. We had to recognize that we had twice as many grams here because we had twice as many moles. And so knowing that, then the answer becomes the greatest in container B, because at constant volume, if it was all 1 liter or 2 liters, it doesn't matter. This is going to have the largest numerator, and therefore it's going to have the greatest density in grams per liter. So that one was tricky. And then here we go with number 10. The reason why I threw this one on here, it says, if the pressure of each gas is increased at constant temperature until condensation occurs, which gas will condense at the lowest pressure? All right, the lowest pressure, meaning it's going to need the least of shoving together to get these things to stay, meaning you are looking for the one that has the strongest intermolecular forces. The strongest IMFs will condense at the lowest pressures, and you would also say at the highest temperatures, even though the question didn't ask that. You didn't have to cool it down that much to get these guys to condense. And so looking at that, the answer becomes right here. This one's going to have the strongest IMFs. It's the longest chain of hydrocarbons. So that became the answer to number 10, butane. Right. All right, and so that question set was from College Board. So that was 3, 4, 5, 6 College Board questions on that particular quiz. It is something that College Board does like to quiz on intermolecular forces on a regular basis. All right, so this video will follow up with everything else we did in class today.